Hello class, today we are going to do a short recap summary of equilibrium. As we've seen through different examples, most of the reactions we've encountered so far have proceeded in the forward direction. We know this because they've been represented by a single arrow that points from left to right, or from reactants to products. As we've gone over equilibrium examples, you've noticed that we now need a way to represent reactions that also occur in the reverse direction. These are said to be reversible reactions. In order to represent that, you need an arrow that now points both ways, from reactants to products and from products to reactants. Now, this arrow is technically incorrect. The arrows that you may see in a textbook or online reading are actually half arrows that look like this. They look kind of like fish hooks, pointing in opposite directions. If you see this, that means it's a reversible reaction. It is more common to see that in a textbook or other official chemistry resource than it is to see something like this. However, this one is a little bit easier to type up and work through when we're dealing with something on Google Docs or something of that nature. So what is equilibrium anyway? Chemical equilibrium is when the rates of both the forward and reverse reactions become equal. We've previously talked about reaction rates and different factors that can affect them. If we manipulate the rates, yes, that means we can change our equilibrium positions. But if we allow the reaction to occur as normal, when those rates in the forward and reverse direction become equal, we've achieved equilibrium. There's a graph at the bottom here that shows the decrease in the rate over time in the forward direction and the increase in the rate over time in the reverse direction. At a certain point, they merge and become equal. At this point, we have reached equilibrium. Reached EQ, equilibrium. Now let's think about this conceptually for a minute. When we are looking at the rate of the forward reaction, it starts off relatively high because I have all reactants and very few products. Since I have a lot more reactants, they need to collide with each other to form products. And when they collide with each other to form products, we see a decrease in the amount of available reactants. So the rate of the forward reaction slows down over time because there are fewer reactants colliding with each other to form products. Meanwhile, there is a buildup of products that are forming that can also collide with each other. And if we have products colliding with each other, then they can break the molecules apart and form new bonds and result in the reverse reaction. So for that reason, you see an increase in the reverse rate of the reaction. Again, when they become equal is when we hit equilibrium. Now notice that is just the rates. At equilibrium, the concentrations of both reactants and products do not change. It appears that the reaction has stopped, but in reality, the reaction is still going. But that does not mean the reaction concentrations are equal at equilibrium. In the graph on the right, we have the amount of reactants or the concentration of our reactants and products over time. We start off with very few products because we started with only reactants. As reactants form, or as reactants react to form products, reactants decrease in concentration and products increase in concentration. At the point where the lines level off and become flat, they plateau, that is when we have reached equilibrium. We see no change, no net change in the amount of reactants or products that we have. It does not necessarily mean they're going to be equal. They can be equal, but it doesn't mean it will be equal. When we're at equilibrium, it's very important to recognize that both the forward and reverse reactions are still happening. There's a really cool simulation here from playmata.com on collisions. If we look at equilibrium, We go back to the first level, we can see some of these things in action. So here's our reaction, H2 and I2, and we see that reversible arrow, and it forms 2 moles of HI. We know the reactants are on the left. We know that the products are found on the right. In the container, they're going to put some particles, and they're only putting reactants in at this point in time. There's only H2 and I2. They're going to start to react. When the reactants collide and form products, that is our forward reaction, you can see that I2 and H2 collided to form 2 moles of HI. Every time you see this pink aura or explosion in the background, whatever, that represents the reaction occurring once. So the reaction here has occurred 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times, which they denote here. We're going to call that the rate of successful forward reactions. Now that more products have formed, there are successful product collisions that can occur as well. So previously we had 2 moles of HI, and they collided to reform 1 mole of I2 and 1 mole of H2. When products collide and reform reactants, that is our reverse reaction. Since this happened once, they now have labeled that as a 1 on the rate for successful reverse reactions. And we're going to continue watching as the collisions occur. You see there's a mix of blue and purple or pink. Now, the same rate, both in the reverse and forward direction, has been reached. We are at equilibrium. Notice equilibrium, as I mentioned, means we did not stop the reaction, but we are reacting in both directions at the same rate, so there's no net change. You'll see if we were able to pause this each time, there are 5 of each pink. Go ahead and pause the video at one of those reaction points and count them just to confirm. Since we have a reversible reaction, we know that reversible reactions will eventually reach equilibrium. In our next lesson, we'll look at Le Chatelier's principle and how different stresses can affect equilibrium.